We have Module 1, Theoretical Yield and Percent Yield with Madison Hartwig. So, to recap Module 1, we have reviewed concepts such as stoichiometry, and within that idea, the mole concept and balancing equations. We will go into depth of another topic within this area and explore theoretical and percent yield, as well as the idea of limiting reagents and a quick review of dimensional analysis and the mole hub. I have chosen to do a quick review on dimensional analysis as we can remotely use it everywhere we do math because it simply uses the relationships of units to convert between them, and you can also use it to check your answers. Before we use this tool, we must ask ourselves a few questions. We're going to want to ask what units are given, what are the units that we want, and then from there, what is the conversion factor that we need to create or find to use. I will lead you through a very brief example of dimensional analysis, and from there, you can check your answers all the time. So to start, we will do a conversion of units through a density calculation. So we are given density in grams per centimeters cubed, but we want to take that up 2 powers to grams per liter. First, we want to realize that 1 centimeter cubed is equal to 1 milliliter, and therefore 1,000 centimeters cubed is equal to a liter. Using this information, we can create our conversion factor of 1,000 centimeters cubed per liter, multiplying this by our value in grams per centimeters cubed. The centimeters cubed will cancel out with the centimeters cubed of the conversion factor, and we are left with 7.8 grams per liter. You have definitely all seen the hub before, as it is a very helpful tool when doing basic chemistry equations. But I wanted to do a very brief review on it, and to make sure everyone has access to this resource. The hub shows you relationships of equations we use in this course, and possibly others, and how the value of moles can take you from one equation to another. Feel free to screenshot if you haven't taken this in your notes from the lectures. Now diving into the topic of focus, we're going to talk about theoretical and actual yield. The yield of something means how much product you can create from your reactants, and ideally we would like to have 100%, but in the real world, reactions are not perfect. As written on the slide, many errors throughout a lab can occur to cause a yield to not be 100%. So the product produced by a reaction that has actually taken place in the real world is your actual yield. The amount produced when we run the reaction through on paper is called your theoretical yield, or in other words, the maximum amount of product that can be produced if the reaction went to plan. But to understand how to calculate theoretical yield, we must first understand the individual components of a reaction and how they contribute to the yield. In order to further explore the idea of theoretical and actual yield, we must first look at the concept of limiting and excess reactants and how we use them when calculating yield. To start off, we have our reactant or reactants that will not be fully used up during the reaction. These are called our excess reactants because we begin with excess of it and we will still have some left over after the reaction has been completed. A limiting reagent is the reactant in the reaction that will be completely used up. We only use a limited supply of the reactant, and we must be careful how we use it as it will be determining how much product we can make. Thus, we focus on the limiting reactant while calculating our yield values. Now, I will show you how to calculate which is which, and you can calculate your theoretical yields. Okay. To solve this problem, we incorporate our knowledge of limiting and excess reactants and figure out which reactant is which. This is the problem we are given, and these are the known values that we have for this reaction. To start off, we will convert the masses we were given in the problem into moles using their molar mass quantities. To do so, we take the mass of the reactant, multiply it by the conversion factor, which in our case will be moles per grams, as we are converting to moles. If we were converting to grams from moles, we would use a conversion factor of grams per mole. Next, we insert the known quantities, which will be 3.60 grams of aluminum for the mass of the reactant. In your conversion factor, you will want your molar mass to be dividing, as it has the unit of grams to cancel the grams in the initial value. We then simply have 1 mole of aluminum on top to complete our conversion factor. We then repeat these steps with the second reactant. Now that we have done that, we can find our limiting reactant using mole ratios. I will only be showing one method to do this, but there are multiple methods to find the limiting reactant. The chosen method uses a mole ratio between aluminum and Cl2, so we can determine how much Cl2 we would need to fully consume all the moles of aluminum, which in our case is 1.33 times 10 to the negative 1. We have the same idea of the thing that we are trying to cancel out in the bottom of our ratio, and this ratio is the ratio of the mole coefficients of our reactants from the balanced equation. We multiply this ratio by the number of moles of aluminum we got from its mass. We will get a value that is either larger or smaller than the previous calculated mole value for Cl2. If it is smaller, then our new value, which is in our case, that reactant is the limiting reactant. But if it is larger, the other reactant would have been the limiting factor. Our final step in determining the theoretical yield of aluminum chloride is to use the number of moles of our limiting reactant, Cl2, that we calculated when converting from masses and multiply it by a mole ratio of 2 moles aluminum chloride over 3 moles of chloride 2. Again, what we are trying to find is on the top, and what we want to cancel is on the bottom. Converting back into grams, we can multiply our last calculated value of moles of aluminum chloride and multiply it by our conversion factor of molar mass of aluminum chloride divided by 1 mole to cancel the mole unit. We then get 8.2397 grams, or to the correct amount of sig-digs, 8.24 grams. Now that we have calculated our theoretical yield, or what theoretically should have been produced, we complete the real-life experiment of our desired reaction and weigh the mass of the products to get our actual yield. In the next slide, we will show how you mathematically compare these two values. Combining all the previous ideas, we get to the arguably most important and useful topic of percent yield. This yield entails a comparison of the two other yields to see how far off your actual yield was from your theoretical yield. To show an example of this, we will use the previous question and its values. Let's say that in our real-life reaction of aluminum and Cl2, we produced an actual yield of 6.97 grams. We can use the equation for percent yield and divide our actual yield by the theoretical yield. You have the mass produced over the max amount that could have been produced. Then we will want to multiply by 100% to get the desired percent unit. When we plug in our values, we receive a percent yield of 84.6%. This is a reasonable yield and actually fairly good. Obviously, something higher is always desired, but in relation, this one is a good yield. If we had something much lower, although sometimes acceptable, it may mean that you have gone wrong in your experiment and lost some of the product or reactant. If you see over 100%, then it is likely that you have an impure product and the added mass is from other compounds that were not desired in your product. As said many times prior, real-world reactions don't always go to plan, and again, many things can contribute to the loss of product and efficiency. This is extremely important in not only the pharmaceutical business as mentioned on the slide, but also in any business that is creating product, as in any waste, inefficiency, or product will waste their money. The process of creating drugs is already super long and difficult, as it can take years of studies and trials before it can be approved by the FDA, and then some more after that. They already are spending so much time and money on their product, they can't afford to lose any available yield and ultimately their money. Although chemists are most worried about the final product, they are also worried about maxing out each yield along the way. Again, because it can take many, many steps to produce a final product, and if you lose some along the way, it can have great effects on the final yield. To also maximize their yield, chemists should always make sure to purify their products after the reaction, as a dilute product will give a higher false percent yield than expected, which is not very useful. Now you have reached the end of the tutorial. Congratulations! We covered Module 1, specifically its components of yield, and now you should be able to calculate theoretical and percent yield, as well as the limiting reagent, and you should know why yield is so important to the economy of industries and much more. I hope you found this helpful. Until next time.